Well, for Professor Brewer's benefit, I'll start by saying Goramil Mahagat, which is Gaelic for thank you, which may convince you that I'm not English. Well, I'd like to thank Mel and Professor Gupta and their colleagues for inviting me back to USC. As I've been telling people, I really enjoyed my time at USC, and I actually miss it. I can't say I miss Los Angeles too much, except in the middle of winter, like right now. So anyhow, it's a real pleasure to be back and to have an opportunity to tell you about some work that I've been doing recently, but it's work that goes back, as you will see, in fact, all the way to my days as a faculty member here at USC. So I'm going to talk about an aspect of testing for faults in circuits, and I'll start by giving you sort of the premise underlying this. I'm going to be looking at a specific class of faults that are referred to as transient or temporary or intermittent faults, and they're characterized by the fact that they don't cause permanent damage to the things they affect, but they can leave errors or cause behavioral changes that in some cases have very serious consequences. And while this is an old issue, it's become more urgent recently because as circuits have been scaled down to the nano level, they're becoming much more susceptible to transient faults. And in fact, being failure prone is a characteristic not only of conventional integrated circuits as they're developing, but also essentially all the new nanotechnologies that are being proposed. And so what I'd like to do is talk about the faults that are of interest here, and then present a very simple fault model that we developed quite recently to represent transient faults. And finally, talk briefly about a mathematical technique, kind of a logical technique, for analyzing the probabilistic behavior of circuits that contain or are affected by such faults. Well, Californians are familiar with faults, including some pretty big ones. Unfortunately, so is Michigan. But I'll pass briefly over that particular fault and talk about faults in integrated circuits. Now, in a sense, if you're not familiar with testing theory, the faults in integrated circuits are really small versions of faults like earthquakes. It's a matter of scale. So you have a broken connection on the left, which is about 1 meter across. On the right, you have a photomicrograph of an integrated circuit, and you see a very clear break in the wire going across there. That's about a micrometer, or a millionth of a meter across. And that's a permanent fault. But there are faults, including earthquakes, that don't really do any permanent damage, at least when they first occur, but they can have very serious after effects, as this tsunami sort of suggests. But going back to integrated circuits, these faults have a lot of different causes. One of the more interesting ones, and somewhat easier to appreciate, is cosmic radiation. As we speak here, we are all being bombarded by the products of cosmic radiation, particularly neutrons. There's a neutron flux passing through our bodies, as well as my laptop here, which can have rather negative effects. They often don't do any permanent damage. We certainly don't notice them. But as we'll see in the case of circuits, they can cause errors or bad states which can linger in the circuit. They can lurk undetected and perhaps lead to major problems. There are some other causes, such as internal noise like crosstalk, manufacturing problems, which are again becoming more serious as technology develops. These can also produce what appear to be, anyhow, probabilistic transient failures. This illustrates the cosmic radiation, and the root cause is high energy cosmic rays from outer space. When they interact with the atmosphere, they produce showers of neutrons, among other particles. And the amount of these, oops, going ahead of myself here. The amount of these neutrons, the flux of them, increases the higher up you are. So the aerospace, the aircraft industry have long been aware of this and have built hardened circuits that are hardened against radiation. But recently, commercial circuits have started showing effects that represent these cosmic rays. For example, one of the auto companies from my new state of Michigan discovered that their electronic parts were being returned as having failed from the city of Denver more frequently than from other cities. And they concluded, and then there wasn't much permanent damage on these, but they had failed. Cars had stopped, hopefully without crashing. They concluded that they were being affected by these radiation-induced faults. And they were having more problems in Denver because Denver's at a higher altitude. It's at roughly an altitude of 1 mile, whereas places like Detroit are much closer to sea level. And the difference is illustrated by this slide here. Looking into an integrated circuit, this shows pictorially what happens when a neutron with appropriate energy goes through. It actually strips off the charge from atoms in the silicon that underlie this transistor. I'm showing a single transistor here. And that can create a conductive path, and that in turn can result in a temporary electrical signal or a glitch, which may then flow through the circuit and cause harm. Here is a transistor circuit, sort of showing from an electrical viewpoint what's happening here. A particular P transistor, PMOS transistor, is the site of the neutron strike. An electrical glitch affects the output. The output should be normally at a 0, but as sort of depicted here, there's a pulse, a 1 pulse, which depends on a lot of factors. How much energy was in the neutron coming in, depends on the logical signals being applied to this gate, and so on. But it's this emerging signal here which can then flow through the circuit that we're worrying about. The transistor will probably recover more or less instantly after this particular problem. So from a logical viewpoint, if you think in terms of zeros and ones, what we're seeing is a 0 on the output that is becoming a 1. But it's only going to stay a 1 for a very short period of time. But if the 1 is captured in the state of the circuit, then it can cause a system crash. And that apparently was happening in these auto microelectronic circuits in Denver and other places. This is not really a new phenomenon. Here's an old study of Sun workstations published in 1990, where the authors tried to collect the faults occurring over a period of several weeks in a set of workstations. And they tried to separate them into permanent faults and two kinds of temporary faults, intermittent, which tend to repeat, and transient, which come and kind of disappear. And what's interesting here is the vast majority of the faults, the number of occurrences, and the time between occurrences is much more serious in the temporary case than in the permanent case. So if you've taken the testing course here, you'll probably spend more time talking about permanent faults than transient ones, but nevertheless, these are and have been the most common. And if we look at the data, again from this study in 1990, we see that the number of system crashes is about 10 times the number of faults that were designated permanent. So it's clear that a large number of transient faults are actually causing this system to crash. The importance of this field was actually recognized by Professor Brewer, who wrote what I think is perhaps the first paper in 1973 on this topic, called Testing for Intermittent Faults in Digital Circuits. And if you don't read this paper for its technical content, you'll find a photograph of Professor Brewer at the end, which I guess tells us that he changed his barber since 1973. But as I mentioned at the beginning of my talk, even though they've been around for a while, they seem to be becoming more common especially in commercial circuits. And this can really be attributed to the developments that are often marked by Moore's law. This is a classic picture of Moore's law, where we're looking at the number of transistors per integrated circuit as a function of time. And this is a log scale, powers of 10. So it's actually been increasing exponentially. And we're somewhere near the end of this curve here. But if you project out another 10 or 15 years, the question arises, what's going to happen? Can you keep shrinking the size of the transistors and the gates in logic circuits forever? So most people would say no, because transistors will, at that stage, around 2020, will be down to the size of molecules. And the flow of electrons will not be a sort of an analog current, but a flow of individual electrons. And in fact, because at that scale, at the atomic scale of electric phenomena, quantum mechanics comes into play, we're going to see a lot of properties which are non-deterministic in form as a result of quantum mechanics. Many people look to new nanotechnologies, so-called, as emerging and sort of taking over. I don't expect that CMOS ICs will disappear, but I think they will be complemented by nanotechnologies, at least if we want to push this graph, increase the density of computer components or whatever they happen to be, integrated circuits, beyond what Moore's law is predicting. So one overriding characteristic of nano devices, and much of it is attributable to quantum mechanics, is that they're failure prone. Why? Because you're dealing with signals, bits in some form, that are embedded in single atoms or even single electrons. And the amount of energy associated with those logical states is extremely small. They may only operate at temperatures close to absolute zero. They may have to be put in a vacuum. And there are other quantum effects, such as the property that if you take a measurement the result you get is not deterministic, it's probabilistic, all of which make testing or even modeling false, to say what's going on, extremely difficult. So I think this is a major challenge. I'm sure some of you will be dealing with issues of fault tolerance in the future, even if Moore's law is no longer considered valid. I'll just mention a couple of nanotechnologies in passing, in part because my work in this area was initially motivated about 5 years ago when I got very interested in quantum computing. And a characteristic of quantum circuits, this is a class of nanotechnologies, but based on quantum mechanics, they have the characteristic that there's a continual interaction between the circuits, systems you're building, and the environment. So in a sense, they're always failing. And you get a very narrow window of opportunity during which you can try and get the circuit to do some useful computation. And most people believe that even with that narrow window, you're going to have to use all the techniques we know from error-correcting codes and so on to make things work. Yet they are perhaps the future, certainly at this microscopic scale of computing. Now here you see what looks like a gigantic organic chemical attached to carbon nanotubes, and although you won't find it in any logic design book, this is actually a very simple adder circuit. It's a half adder, and these sort of benzene-like rings here are actually wires, and there are individual electrons hopping from say atom to atom through this, and the end result, surprisingly, is that you're getting a couple of functions out which correspond to the addition of 2 bits, what a full adder does. But the scale here is in the physical dimensions of this are a few nanometers, billionths of a meter. So this probably represents about as complex a biomolecular logic circuit as anybody can build these days. So we have a long way to go before we can do something like a microprocessor. Quantum computing depends on storing information in the form of a state such as the electrical or optical state of an atomic particle. The spin of an electron is one example. And you can think of it as having 2 states, the 2 major states, up and down. We use these to denote 0 and 1. And they have all kinds of interesting properties. Unlike conventional circuits, signal doesn't have to be just a 0 or just a 1. It can be a mixture of the 2, a superposition of 0 and 1. And this makes it possible, at least in principle, to do parallel processing on all possible states in an n-bit register simultaneously. And a discovery was made in the mid-1990s that a very important problem called prime factorization can be solved exponentially faster using quantum computing techniques than using any known conventional technique. And this is pretty much the killer application that has been driving research and interest in this field. Measurement, as I mentioned, has this property of sort of destroying the quantum information and producing a result that is one of the stored results, but you can't be sure exactly which one. But you can work with probabilities. But the combination of this means that combination with small size, low energy level, uncertainty in the outputs, means that we're really going to have to approach some of these nanotechnologies from the perspective of dealing with failure from day one, or actually from nanosecond one. The really bad news is that they're very hard to build, but not impossible. So let me just finish this little bit of background by showing you some physical circuits that were developed at Michigan in the physics department by colleagues there. Here you see a bunch of individual atoms trapped in something called an ion trap. They're charged electrically, and the electrical states can represent 0 and 1. And they're all lined up because they're repelling each other, and they're enclosed in a cylindrical field that prevents them from escaping. And they can interact with each other, and with a laser, or a bunch of lasers, you can actually do computation on this. The first time I used this slide from Professor Chris Monroe, this was the state of his art in his physics lab. This is a room-sized piece of equipment, and if you zero in, here, you find a couple of electrodes, and in there are two quantum bits or qubits of information. And it's all in a vacuum, refrigerated, and the glass screen in front allows a laser to be used as an input-output device. But last year, an integrated circuit development resulted in an IC version of this same machine. So it's still only a 2 quantum bit device, but still it suggests that we may see practical devices in the foreseeable future. How soon? Nobody really knows. Okay, so there are various motivations then, both coming in the future with nanotechnology and coming right now with current CMOS integrated circuits that motivate interest in transient faults. So what I'd like to do next is talk about modeling these faults. And Mel accused me of developing very simple models, so I'll show you a very simple model of a transient fault and talk about some potential applications for it. Let's go back and see again what kind of things happen when a radiation strike hits a logic circuit. Well, if things are set up properly, or happen to be badly set up, the signal produced by the strike, which I'm showing in this little red glitch here, can propagate through the circuit. And so it's moving from gate to gate. It's finally coming to a latch, and if the timing is right on the way the latch is clocked, it can be captured. So instead of getting an expected 0 signal on the output of this latch, we have a 1. Now, by this time, the strike may have, its direct effect may have disappeared. The circuit is perfectly normal again, but the state, the output of the latch is wrong. So we see a glitch propagating through the circuit. And the conditions for this kind of error capture are rather subtle. And they include having enough energy to affect the gates in question. The path of propagation has to have precise signals on the other inputs to the gates, besides the one that things are propagating along. So, for example, if we had a 1 here instead of a 0 on this unaffected input, that would block propagation. So the logic path must be sensitized in the classical sense. And the final pulse here must arrive in sync with the clock timing of the latch so it can be captured. Now, since satisfying all of these conditions in different parts of the circuit won't occur too often, not too many of the particle strikes actually produce an error. And even if they do, the error may not be serious because that particular state may not ultimately affect the operation of the circuit. So anyhow, we got interested in the question recently of how do we model the transient faults like this and the errors they produce. The classic model for permanent faults is the single stuck-at fault model. And that says that any logic line in a circuit can be permanently 0 or permanently 1 after a fault occurs. So most test generation methods are based on this. But it doesn't account for, it is a permanent fault model, it doesn't account for transient or indeed any time-dependent effects. So to deal with that, we're making using a very simple extension, if you like, to say that we'll talk about, instead of a single permanent fault, a single transient fault. And this has two features, one of which is sort of obvious. We'll say that it's like a single stuck-at fault, except that it only lasts for a limited period, like one clock cycle. But what's not quite as immediate, we'll also associate the total state of the circuit, which means the input combination and the stored internal state, the state of the latches and flip-flops, will also be part of the definition. So an STF, then, single transient fault, induces a very short-lived, state-dependent change, a flip to 0 or a flip to 1, that can occur on any line in the circuit. And since we would like to be able to analyze these in a technology-independent way without knowing about such things as the actual neutron flux level, in this room at this time, they vary with circumstances, we'll just assume that they tend to occur randomly. And with no other information, we can treat them as being equally probable. Again, here's the definition and how it intuitively relates to a strike. We're going to put into the model the effect of the strike, which is to change a 0 to a 1, and we will capture the conditions in the circuit by capturing the input combination, the primary inputs, and also the state. And if we consider all possible conditions of this kind, we'll get a set of faults. So this is one where, in fact, it can propagate, I believe. No, it's blocked. Yes. Thank you. That was a little test to see if Professor Brewer remembers his logic. He clearly does. This one, will this one propagate? Yes. So there are lots and lots of possibilities. And the first objection you might say is, well, that's all very well, but the number of such faults is going to be enormous. In fact, it will be the number of states times the number of input combinations times the number of lines times 2 for stuck at 1 or stuck at 0. But as I'll show, we can actually deal with those numbers. They're not as bad as they might seem. And furthermore, we can do sampling if the number of possible faults is too big. But it's also easy, since there's an obvious relation to the standard permanent stuck-at fault model. We found it very easy to adapt existing CAD tools for simulation of faults and simulation of test generation so that they can handle these STFs. And we also observed that, in response to another objection, while they may not precisely model physical transient faults, it doesn't necessarily have to do so if it can provide useful information about the impact of transient faults on circuit behavior. And it's well known that the standard stuck-at faults, the permanent faults, also have that characteristic. They're used throughout industry as the standard way of measuring the quality of tests and actually generating test patterns to detect or locate faults. And although we haven't explored it very much, it's a concept that can be extended. You could make the faults persist for more than one cycle or assign different probabilities to different faults. And we're looking at a number of potential applications. We're very much interested in another topic that we can attribute to Professor Brewer, and that is error-tolerant design, as opposed to the traditional fault-tolerant design, where you don't expect perfection from the circuit, but there may be error conditions that you can tolerate because they have an insignificant effect on the behavior of the circuit. And if you can tell that and design for that, you can produce better and probably cheaper circuits. So this we're viewing as a model for estimating things like how long can a fault, a transient fault, or an error it produces persist in a circuit without appearing at the output. That's the error latency. It's of interest to measure reliability with respect to transient faults, and of course to go from evaluating reliability to synthesizing ways in which we can increase the reliability. So to give you a quick flavor of that, I've got a simple example here where we'll show that we can do some mathematical analysis of these faults, at least in simple cases, and for more complex ones we can use simulation. So I'm not going to talk about sequential circuits, but combinational circuits. Now in this case, there's no internal state, and the STFs reduced to a simpler form where we have a stuck-at condition and then just the primary input pattern defining each fault. So we can consider the following question. What is the probability of an error on the individual outputs, or collective set of outputs of a combinational circuit, if all the possible STFs can occur in the circuit with equal probability? This will give us numbers that I think in at least a few useful cases are very helpful in gauging the sensitivity of the circuit to actual transient faults and in, we hope eventually, in designing for error tolerance. Some simple results. You always start with simple cases. For individual gates, it's a simple exercise to compute the error probability of the output. It's a function of the number of inputs, and it's a matter of counting the number of STFs and which ones are able to affect the output. It's worth noting that if the STF affects the output, causes an error, then whatever input combination you have is actually a test for the circuit. So by counting the tests for all the possible STFs, you can get these numbers. And it turns out that the best possible case, the most resistant to transient errors, is a gate of the and or not variety, and the least resistance type of gate is an exclusive OR, or exclusive NOR. They propagate information through. So here's just a quick example. Ripple carry adder, which you remember from 210. Is that still the number? Introductory logic design? 201. Sorry, 201. Yes. Oh, well, either I guess it became easier, or the professors got smarter, or something. But that was the first course I taught here, Introductory Logic Design. To show that nothing has changed over the years, I'm teaching Introductory Logic Design at Michigan at the moment. The same notes, which are no Brewer's notes. So this is a case where it's a very regular circuit, and you can actually, as I show here, derive a formula. Somewhat complicated one for the error outputs. If you can't do this, you can just do simulation. And you can collect data like this, which is showing for ripple cariatas of different sizes the probability of an STF-induced error on the output. And it won't tell us too much, but it does tell us, for example, that the further you go towards the most significant bit, the less likely you are to get an error. It also points out something not quite so obvious, is that, sorry, yes, the numbers get bigger because you have more circuit behind that's generating it, yeah. For a general case, we can easily construct a formula that we can simulate using slightly modified standard tools to calculate error probabilities for fairly large circuits. For lack of time, I'm not going to say much about these faults in sequential circuits, except that they raise some interesting questions like how long does it take for an error to disappear from a circuit? And in other words, what's the probability that a sequential circuit will recover automatically from these errors? And we can analyze these using a technique called Markov modeling, which you will find in the original paper by Professor Brewer, among other sources. We've also applied this, and we're presenting this at a conference in May, to the question of measuring or even improving the reliability of a circuit by selectively hardening gates to reduce the error probability. And the kind of thing you find is shown by this data here. We're asking the following question. If we want to reduce the output error probability, average overall outputs, to a lower level, what percentage of the gates do we have to make resistant to errors? And there are known techniques for doing this. And so the yellow one here is for reducing it to 0.1. And it varies a lot with the circuits. For this particular C880, for example, something close to 20% of the gates have to be hardened. But if we want to reduce the output error probability to 0.01, then it jumps up to like 60%. All right, so move, please, yeah.
That was not for, under what assumptions was the probability of 0.1? Calculate.
Well, it's a target number. And it was,
Does it have a physical meaning in that?
no,
Radiation.
no, but it could come from a physical source. But here it's just to get a feel for how the overhead is sensitive to the faults. But we hope that if we have real numbers, we can put them in and scale them appropriately. Okay, so the last part of my talk, and I'm looking at my watch here, which Detroit Airport Security was instrumental in breaking last night. It's still working. I'd like to talk about another technique for addressing computation with transient faults, or in fact more generally doing probabilistic calculations in logic circuits. And this work stems directly from research we were doing a few years ago on quantum computing. One result of which was we developed a simulator for quantum circuits. And when you deal with quantum circuits, you have to use linear algebra to analyze the behavior. And there are certain operations like the tensor product, which are not very familiar in classical circuits, but are fundamental in quantum circuits. And we found some connections between the two. So I'll be talking about classical logic circuits, but using these ideas from quantum computing. This is another area where you can find papers dealing with probabilistic analysis. A reviewer told us a year ago that we had gone back as far as Professor Brewer's papers, but in the electrical domain there are even older papers that talk about electrical analysis. Anyhow, this particular tool, you might say, that we call the probabilistic transfer matrix, we introduced a few years ago and have been exploring it since then. So the idea is to represent a gate or an entire circuit by means of a matrix. And here is a NAND gate with two inputs. And this matrix has a row for every input combination and a column for every output combination. And if you write in this form, we're saying the input's 0, 0, the output's a 1. And this is really equivalent to the truth table for the circuit. However, if we interpret the zeros and ones here as real numbers, we can also interpret these as probabilities. So a 1 here says there's a 100% probability that if we apply 0, 0 here, we'll get 1 on the output, and a 0 probability we'll get a 0 out. And now we can play with the numbers. We can put in different numbers to reflect errors that might occur in the circuit. So keep this input-output relationship in mind. And that brings us to the notion that we call a probabilistic transfer matrix. So each entry, again, gives you an input-output relation, but now we have a probability. And so what this is a PTM for the same NAND gate, but it describes its behavior under the assumption that for every input-output combination, or there's a probability P of getting the wrong output. So here, well, take 1, 0. The wrong output is 0, probability P of getting it, and then 1 minus P of getting the right output. So it represents a faulty NAND gate with this probability of outputting the wrong value. And we can define a surprisingly large number of different faulty behaviors by using PTMs, including deterministic ones, in fact, including the classic stuck-at fault, and others that are more complex. And this shows some examples here. Here's the original normal NAND gate. Here is a NAND gate with a stuck-at-1 fault in one of its inputs. So in fact, 0, 1 is a test for that, and it will flip the outputs, or the output probabilities. Here is a transient stuck-at-1 fault, where it looks just like this one, except that we now are putting a small probability on the wrong output, namely 0.1, 10% probability of the wrong output, 90% probability of the right output. This is an example where we've just flipped the zeros and ones, and this would correspond to a wrong gate fault, where a NAND somehow magically changes into an AND. An important aspect, too, is that the interconnections, the wiring networks that connect gates, they also are representable by PTMs. So for a crossover down here, there are 4 input combinations. We get this permutation matrix that simply describes this behavior. If we have 0, 1, we'll see 1, 0 on the output. And again, while the normal case seems like a redundant way of representing a truth table, it's by changing the entries, we can capture error probabilities. Okay, now how do we put all these PTMs together to get the PTM of the circuit? If we have 2 gates in series, connected one feeding the other, then the PTM of the series combination is just the matrix product of the 2. You can verify that quite easily. If we have 2 signals or 2 components, like this gate, AND gate, and this wire, in parallel, we need an operation called the tensor product, which essentially merges all the states that we can get from the combination of the 2. Or mathematically speaking, here's the PTM for the AND gate, the tensor product operation, the PTM for a wire, which is just an identity matrix, and the tensor product defined in this way multiplies every element here by the entire matrix over here, and we get this larger matrix. So the matrices are big, since their dimensions are the same as the number of input and output combinations. But this tensor product is, along with the matrix product, the ordinary matrix product, these are the basic operations for combining PTMs. And what good is this? Well, one nice, I think, theoretical aspect is we can describe behavior in a very concise way using multiplication and the tensor product. So for this example, we're sort of going through the circuit slice by slice. The F here is a fan-out gate, capturing fan-out as a matrix. And then the swap is a wire also. Then we have a NOT, which has its own matrix. A couple of NANDs, and finally the output NAND. So this is our matrix expression that captures precisely the structure of the circuit. And if we plug in numbers, including errors that might arise from transient faults striking them, we can evaluate this and get the error probability on the output. So let me jump and just show you a very simple case. We're going to represent input probabilities by a vector. And here we'll assume that the inputs have equal probability. So each wire has a 50-50 chance of having a 0 or 1 applied to it. We form the tensor product of the 2 wires here. We get a matrix which just says that there's a 25% probability for each of the 2-bit input combinations. Then we take our gate PTM, and this is another NAND PTM with a small error probability associated with it. Multiply the 2, and we get the exact output error probabilities. This is ordinary vector matrix multiplication. And it's a very small probability, so there's a little bit bigger chance of getting a 0 than normal, which would be 0.25, and a little smaller chance of getting a 1. So there are a lot of computational issues, and my students who are working in this area have devoted much of their time to issues of memory efficiency, data representation, and so on. And in the course of our quantum computing work, we were actually dealing with matrices where the entries are not just real numbers, they're complex numbers. And so we developed a simulator that is designed to handle very large matrices of complex numbers. And this applies quite well here to the PTMs because we can adapt a technique which goes all the way to the CAD field, design automation, originally binary decision diagrams, which were extended to algebraic decision diagrams. We extended them to quantum decision diagrams. They provide a very compact representation for large matrices, as long as there is some structure that they can exploit. So our simulation of the PTMs, the way we actually handle them in a computer, is not by storing matrices in any traditional form, but storing them in this graphical form, which is called an algebraic decision diagram, or ADD. And in fact, in that form, I won't go into the details, you can do operations like tensor product and matrix multiplication on the compressed form without expanding it to this possibly very large matrix form. And we have applied this mainly to calculating reliability numbers for circuits. And there are other techniques for doing this in the literature. Most are heuristic in that dealing with very large circuits, but making approximations that we have found are often quite inaccurate. While PTM operations won't extend to very large circuits, like to say we can handle small and medium circuits, they do have the virtue of being accurate in the sense that they retain all the information that's incorporated into the models. But other applications that we're looking at include finding critical components in a design. If you know where the error probability is highest, then you can perhaps redesign that part of the circuit to make it less sensitive to the errors. We're interested in designing fault and particularly error-tolerant architectures with an eye on nanotechnologies and also another eye on quantum circuits. And perhaps devising online testing schemes that will find out something about the occurrence of transient faults. This is just calculating a reliability figure, referred to as fidelity. I just want to show that this can be done in terms of PTMs. And it involves a number of matrix operations which our simulator has to be able to handle. The end result is given an input distribution, error probabilities associated with the gate, we can calculate a number which is sort of a quality indication for that gate. And we did some experiments, collected some data, as publication requires. So let me summarize at this point. We feel that transient errors are an increasingly significant source of failures in both current and future logic circuits. We need models like the STF model to have technology-independent ways of analyzing them. And clearly we would like to be able to use them also to learn something about the technologies that are coming along. And we can use techniques like matrix-based computation, the PTMs I mentioned, for analysis purposes. And there are lots of potential applications in both analysis and synthesis of logic circuits. The obstacles are where we stand at the moment, or we don't fully understand the theory, but we have a reasonable grasp of it. Scaling the methods up to large circuits with hundreds of thousands of gates is difficult. But techniques from design automation like data compression, using decision diagrams and so on seem to be very helpful. And finally, we need to explore applications. And I think there are some interesting applications, and I expect we'll see many new ones in the future. And finally, I'd just like to acknowledge the grad student, Smita, and a colleague, Professor Markov, and a couple of colleagues in the University of Freiburg who were kind enough, among other things, to host my sabbatical there a few years ago, and I've been working with. So with that, I'll conclude, and thank you for your attention. Questions?
One question. You said earlier in your talk that military understands this problem. It's more computation, flying up in space and satellites. They have developed rad-hard techniques.
Yes.
So explain a little more about those rad-hard techniques and why we're not expect to have some ability to put a neutron-resistant thin film over our chips and say it's not.
Yes. I think there are two reasons come to mind. Both have to do with expense. One is that if you make the components bigger, the transistors and the gates bigger, they are more resistant to the radiation. It takes more energy coming in to affect them. But if you make them bigger, they take up area on the chip, and that's expensive. Another approach is to use special design techniques that either coat, in a sense, the circuits to block radiation, or change their profile so that they can sort of dodge, if you like, the bullets coming in. But those are also expensive. They're non-standard fabrication techniques, and they add to the cost. So assuming NASA and the military have unlimited budgets, which they often look like they have, they can afford to spend more money on radiation hardening. Take the auto industry. Their goal is to produce the cheapest possible circuits. So there's a big disparity, which may be 1 or 2 orders of magnitude in cost. Chips, and there are hundreds of them in your typical car, even little microprocessors. The car companies are paying less than $1 for these. It's arguable that the military even recognizes $1 as a unit of currency. $1,000 toilet seats and so on. So there is a cost issue there, which I think is important. And at least until now, I would say, the production of rad-hardened, radiation-hardened circuits has been a very limited activity of some small number of companies. Mel, can you comment?
No, I don't want to comment on that one.
Okay.
I had another question.
Please.
Are you happy with that? It's expensive.
But if I may comment on that.
Yeah.
But there is an enemy within which you can't protect necessarily by shielding yourself, because now there are internal sources of protection.
Yes, that's right. Yeah, that's quite true.
You implied that on this probability, especially, you're doing things similar to signal probability differently.
Yes.
The problem with that was there were approximations and heuristics. You implied that your technique doesn't have those kind of errors.
Well, the signal probability, yeah.
The
Sorry.
problem there was reconvergent fan-out.
Yes.
So my question is, in your technique, when you have reconvergent fan-out, you get the correct answer or an approximate answer?
You get the correct answer if you capture the reconvergence. So what I showed you is going slice by slice through the circuit. That is capturing fan-out and reconvergence. But in addition, the early signal probability work was mainly concerned with calculating the probability of 0 and 1 on a given signal. It doesn't address the issue of propagation to the output directly, which depends on other conditions. We're also trying to capture that here. So the scaling, in those days, the early papers by McCluskey et al. 20 years ago didn't really consider scaling up to very large circuits. And the techniques of assuming independence on inputs so you didn't have to worry about reconvergence are very error prone. They introduce serious errors in the computation. So I would say currently we're avoiding that by maintaining the reconvergence. It's still an open question, I think, how you can approximate that accurately for very large circuits. And it's a valid question because actually some of the tools out there, I think, are suffering from the same problems that existed in the early work. Sandy.
Tools that you described. How to find more reliable circuits. And I guess more specifically, can you get any insight from traditional error-corrected codes, Solomon, linear codes, or other redundant computing techniques for analytical?
One way the tools have been used is the following. You can, there are many techniques for synthesizing circuits that will take a portion of a circuit and resynthesize it, say, to minimize the area. We and others as well have been looking at synthesis for reliability, where the idea is that you take a portion of the circuit and use the tools to calculate a change, make a change in the circuit locally that doesn't affect the overall function, but may affect the reliability. And then calculate on the fly the change in the reliability. And it is possible, but the jury is still out on the effectiveness of this, I think, to, in that way, increase the reliability as measured by these tools. It's an interesting example, actually, illustrating that if you have really good CAD tools that are extremely fast, you can incorporate them into a design space search mechanism for a variety of very complex problems that you can't really handle using other techniques. Todd?
As you are very well aware, in quantum computing, no one expects to be able to build computers that will be fault-free.
Yes.
And so then on developing.
Yes.
One thing that's come out of that is that if quantum circuits can correct some errors passively.
Yes.
So that the error happens every day. So equivalence. So we found that you can define sort of that instead of uniquely encoding your data in one code word disk, an equivalence class code word all represents thing. Inherited to move to RAM with the class doesn't.
Yes.
So this idea of error tolerance, kind of like it actually has some there cards are circuits are all invertible, whereas presumably error tolerance go away as you but wonder if it has to be a fraction of error. Maybe, redundant.
Yeah. Well, traditionally, Professor Sawchuk mentioned fault-tolerant circuits, all of which are of great interest. The traditional fault-tolerant circuits try to block every possible fault in the circuit without making any distinction between those that produce tolerable errors or those that produce critical errors. So I think now people are realizing that we should make a distinction between the two. Now, Brewer has been a great advocate of this over the last few years, and reconsider, really, fault tolerance in the hope that you can get error tolerance, which I see as having two benefits, more flexible or simpler correction circuits, or designs that are not as costly as the traditional fault-tolerant designs, and also better understanding of the relative impact of different faults. And I would not be at all surprised if again, ideas from your quantum computing research do indeed have a useful analog in classical circuits. They're different in many ways, but there are a lot of similarities that we shouldn't neglect between quantum computing and classical.
Let me go back to Sandy's question and phrase it in, so I think thought took it in one direction. Let me take it.
Okay.
So let me think about this from the point of view of the technicity. If I took an encoder for, say, an input, I took the model of the channel. So I took the circuitry for that. I took the Hamming, I took the channel. I took the channel model for, input binary symmetric channel. Representation symmetry. And I took the decoder. Could I analyze the circuit for this entire system by using a method and actually compute probability of incorrect input under different channel conditions?
If you can express the problem in terms of linear algebra.
But I'm giving you a circuit for the input.
Yes.
I'm giving you the channel which is binary symmetric channel, whatever that channel is.
Yeah.
Which is a PTM-like representation.
Yeah.
I'm giving you a decoder which is a circuit.
Yeah. Yeah, I think it should be possible. I don't see any reason in principle why it could not be done. Well, what do you see as a problem or difficulty?
I think it can be done. And
Yes.
Just probably complexity. I don't know where the complexity is driven in there.
You're building error correction circuit, and instead of simulating tiny individual components, logically,
Yes.
elements in actually live from
Yes.
despite larger circuits.
Yes.
Of course, include those as well. I was just talking about the classical version of the problem. The error was only happening with it.
My question is, come out with something
errors left in the contour.
Yes.
Talk about exceptions where it may last more than the contour. I'd be interested in exceptions where it lasted shorter than the contour.
Yeah. The challenges of doing that are you're going to have to measure delays. And it's not easy to do that in that accurate models of delays in gates and wires tend to greatly increase the complexity of the problem. And I would argue that it may not be necessary in many cases because in sequential circuits, the issue is capturing the error. You don't really care if the error propagates to the circuit. What you care about is the error captured in a flip-flop. And that depends on the clocking of the circuit.
He doesn't have clocks.
I was just
If you're an asynchronous person. Yeah.
have a node
Yes.
sensitive to the clock
Yeah.
more time than other nodes.
Mm-hmm.
For example, in the path between that node and the clock, there are many different paths of different lengths.
Yes.
Versus where there's only one path and one.
Sure. Yeah.
So clearly, when you're looking at your logic for where to harden this information, is quite useful.
Yes.
Because you might want to harden a gate that's more sensitive over a longer period.
That's true. Yeah. There's nothing, I think, in principle to stop you from doing that, but in practice, the complexity of the model, which is already very high, we're already struggling to scale things up. If we add in delays, we won't get so far. We'll have to retreat.
Okay, let's thank Professor Hayes and